Hello, I'm Greg Maxwell, one of the developers of the Bitcoin system and Bitcoin reference software. Since 2011, I've worked on the system, facing many interesting challenges and developing many solutions to many problems, adapting and growing and maintaining Bitcoin, along with a community of other technical contributors. Today I'm going to talk about some of the interesting challenges that we faced in adapting Bitcoin, and I'm also going to be announcing some new project initiatives that we're making available to the public now to help address some of those challenges. Blockstream was founded by a collection of technical experts in the Bitcoin space who were looking for a way to organize and fund the development of complicated technical solutions to important problems, and to also take the ethos and trustlessness and values of the Bitcoin system out to the wider world and to apply them into new places. So first I'm going to talk about some of these challenges that we've had in bringing Bitcoin technology to more applications. And then I'm going to talk about Elements, which is our project that introduces some tools for dealing with these challenges. And then I'm going to talk about the specific interesting features that we're using Elements to make available. Before talking about the challenges we're facing, I thought I should level set with a view on what Bitcoin is actually accomplishing. So traditional systems of money have this property where they require trust at all levels. You trust your bank, you trust the parties that move funds from place to place, you trust the central banks to have good economic policy. And this trust is very costly to maintain. It requires constant vigilance, and it's also easily violated and unpredictably violated. So this makes the existing monetary systems that we have in use less useful. So Bitcoin poses a potential solution for some of these problems. And it starts with the idea of what if we replace the systems of money that we're using today, or augment them, with a system that is based purely on mechanical rules, mathematically defined and enforced by computers, rather than just human processes. And by taking the human out of the loop, we potentially reduce the influence of politics on the system and have something that is much more dependable. And the idea of building a digital currency out of computers and mechanical rules has been around for a long time, and people have been seriously working on it since at least the 80s. But it's not as easy as it might sound. It runs at odds with something of the fundamental nature of information. One aspect of digital information, and information in general, is that a copy of a piece of data is every bit as good as the original. And information doesn't inherently have an owner that can control it. We can only achieve those via overlays on top. And if we think about building a monetary system out of information, well, for our money to be useful, it has to have controlled supply, or otherwise I would just say, oh, okay, I have $1 trillion of the money. And it also has to have ownership so that someone can't come along and take my money. And those criteria are sort of fundamentally opposed to how information actually works. And if we're going to build this system out of computers, well, computers are controlled by people, and people are pretty good at ignoring the rules when it suits them. So the positive news is that after decades of effort and people believing the problem was impossible, it was discovered one possible path to do this, and that's what Bitcoin is. So Bitcoin employs cryptography and economic incentives to build a system where the rules of the system have true force, independent force, that can exist even without or against the popular will. Now, you can look at this as basically handing over control of the system to computers, where the computers are really in charge, not just following the orders of people. And that's pretty cool, because you can make very strong promises about what that system will do. But the bad side is that, well, computers are in charge, and nothing can be as infuriatingly stupid as a computer. And there's been plenty of science fiction that has informed us about the potential dangers of putting computers in charge of things. Fortunately, Bitcoin's remit is pretty narrow, and so the thing it's in charge of is pretty specific. And it doesn't necessarily have a lot of danger, but it does have a fixed set of rules. And so if we had perfect foresight, perfect engineering, if we could foresee all of the consequences of our decisions when we built the system, we might be able to build a system of money where the rules were completely defined at the outset, and which never changed, and which everyone could count on for all time. And that would be pretty interesting. But the reality is that we don't have perfect engineering, we don't have perfect foresight, and people don't always agree on what their values are. And so, since we don't have these things, mistakes were made, and Bitcoin originally didn't even correctly enforce ownership. At first, because of bugs, anyone could spend anyone's coins. So needs change, problems are found, the world changes, and sometimes people have contradictory requirements. And so we face this challenge where Bitcoin's very nature is to be hard to change, and that's how it's trustworthy and survivable. And you don't have to worry about who created or who controls it, because no one controls it, it just is. But those same qualities also make it very hard to adapt Bitcoin to the changing needs of the world. So some people have sought to address this particular problem by creating new alternative digital currencies. They're called altcoins in the Bitcoin space. So they're just copies of the Bitcoin system, which work by taking the Bitcoin source code and changing the name on it, maybe adding some new functionality, or maybe not, maybe adding a picture of a dog. Some have been pretty interesting, but most are pretty boring. They're just a reboot. And why would people just reboot it? Well, when Bitcoin came into existence, it was worthless. And then over time, as people saw the potential value, they started trading Bitcoins for larger and larger amounts of money. So this creates the potential for a speculative race where people want to get in and hope that it becomes valuable in the future. And this has incentivized the creation of many altcoins, even ones that really have no otherwise reason for existence. A problem with this is that there's no natural stopping point. Right? First there's Bitcoin, then there's Fucoin, then there's Barcoin, then there's Bazcoin, then there's Barfcoin. And someone from the outside looking in might look at this and say, well, why am I going to use this Bitcoin stuff when tomorrow it'll be worthless because someone wants Barcoin instead? And that comes to this point that the fundamental value of a money-like good is the fact that other people will accept it. That you know you can take it today, and then you can give it to someone else tomorrow, and that they'll value it. So the value of a money-like good comes from its network effect. And if you start up new cryptocurrencies all the time, all you're doing is fragmenting the network effect. We're also left with the problem that fundamentally, this is no different. If you build a new system and it's very decentralized and it's very widely adopted, it too becomes hard to change. And so the reboot is left with the same problem Bitcoin has, that it's difficult to change and adapt to new needs. So I wish people luck who are trying to do this, but I don't personally think that it's a great and sustainable way to build and deploy new technology to the world. So what else can we do? Bitcoin was designed from its very start to be able to be extended in a way that's compatible with the existing system, in a way that doesn't override any of the existing rules but adds new ones. And one of the things that Bitcoin has built into it is a system for smart contracts. Smart contracts are this idea that when you pay someone in Bitcoin, you don't just say who you're paying, but you can specify a computer program that decides if the payment is to be permitted. This is a smart contract, right? The contract is the program. Now, this doesn't eliminate or make easier the difficulties in establishing contracts that achieve what you want. And in fact, it makes it harder, right? When you have to write a program that enforces your rules, you really have to get the program right. But what it does is it makes the enforcement effortless because the smart contract is enforced by the Bitcoin network. So the Bitcoin network acts like this perfectly trustworthy artificial intelligence that executes the contract and faithfully does whatever it says, good or bad. And what this means is that in many environments today where you cannot get enforcement for a contract, you make a contract over a cup of coffee, well, you could try to enforce it, but your counterparty will laugh at you and the courts will laugh at you and the contract is worth nothing. It allows you to have a system where the contract is inherently enforced by the system itself. Unfortunately, the smart contracting capability in Bitcoin is somewhat hobbled by bugs. The original system had limitations and problems. But it's possible to fix them and to improve them in a compatible way. And we use a mechanism called soft forks, which are backwards compatible additions to the rules of Bitcoin. And we've used soft forks several times to deploy new features into the Bitcoin system. So the 3 type addresses that are widely used today are an example of a soft fork that we did in 2012. There's another soft fork right now, change in the signature encoding, which is sort of technical minutia, but it shows that this process works and we can use it to deploy updates to the system. But even given the process of soft forks, it's very difficult to do updates in a live production network. In Bitcoin, it's a system that's used by many, many people. It has a sort of market cap, if that's how you want to measure things, over $1 billion. And the very design of the Bitcoin system was to be beyond influence. And so it is just hard to update. And many of the updates that you'd like to do are just easier to do in a whole new system where you don't have to worry about potentially disrupting any of the things that are going on. Bitcoin has built into it a mechanism for very efficiently proving to someone that they were paid in the system. And this is called Simplified Payment Verification, or SPV. And it allows you to have something like a vending machine that listens to the Bitcoin network and with very little data sent can learn that it was paid. It has to make some security trade-offs in doing this. It has to trust the network to be honest to it, the network as a whole at least, but it's very efficient. So what if we combine this notion of simplified payment verification with smart contracts? What if you write a smart contract in Bitcoin that allows coins to be moved only if another transaction occurred? And this is a little abstract, but the mechanism here is something we call the two-way peg, and it's described in the white paper we released last November. What we can do is use this two-way peg mechanism to build something called a sidechain, a parallel Bitcoin network that is similar in Bitcoin in its operation, but separate, maybe with new features. Then you can take some coins on the Bitcoin network and freeze them, and then the sidechain network can observe this frozen coins and allow you to transact on the sidechain network. When you're done transacting there, you make a transaction that effectively moves the coins back to Bitcoin, that releases them out of the smart contract that's holding them on the Bitcoin network. So in doing so, we can gain the freedom and agility of having multiple networks without rebooting the Bitcoin network effect, without changing to a new currency. So multiple networks, but one currency. And this would allow us to do new, risky, experimental, or niche applications and put them in their own networks. So I'm happy to introduce Elements, which is our project to advance the state of the art in Bitcoin using this Sidechain's two-way peg mechanism. And the idea here is a no-holds-barred use of exploratory technology where we'll be able to try out new things and deploy them on a network that can be used with the existing Bitcoin network. Now, going straight into the Bitcoin network might be a little bit of a leap. And so we're first using, with Elements, we're first using the testnet sidechain. So testnet is an existing parallel Bitcoin network that's used for testing the Bitcoin system. It's existed since 2010 or so. It's used by the developers of Bitcoin software, and by social convention, the coins in testnet have no value. So you can trade them back and forth, and it's widely used. And with Elements, what we're doing is producing a new sidechain that will use the two-way peg mechanism to transfer testnet coins from the testnet network into the Elements sidechain, which we're calling Alpha, and back again. So this is free software that will be open to everyone to open new avenues for exploration. And we've included into it a bunch of interesting features, which we're calling Elements. And this is all neat and all, but one thing to keep in mind is that it doesn't currently have a lot of quality assurance. And that's actually a good thing, because one of the major barriers in deploying technology in Bitcoin is all of the work you have to do to make sure that the software is trustworthy. So it's very refreshing to be able to work on some technology and experiment without having it potentially impact a billion-dollar economy. But still have a way to put it into production use. So I'd like to talk a bit about each of the top-level new features that we've put into Elements. So each of these new features is effectively a single person's experiment, although we've cooperated some for review and enhancing the development of the software. And I hope that people will pick this up, find the software useful and inspiring, and contribute their own experiments to the work. But as I said, I would strongly recommend against using the current code with a real with-value cryptocurrency network. So the first of the elements I'd like to discuss is the deterministic peg. And this is that two-way peg mechanism that lets you bring testnet coins into the Elements network, into Alpha, and then back again. So this is implementing the stuff we described in the Sidechains white paper. And the basic mechanism is that you can make a transaction on testnet, and wait for 10 blocks on testnet, and then signal the move in the sidechain. There is a 144 block confirmation period on the sidechain that allows for someone to prove that the proof that you gave to it wasn't actually valid. And if that passes, then the coins are allowed to move. Now, this is all fundamentally limited by the insecurity of the testnet network itself. Because testnet only has a few users, it's not really a decentralized system, and the security is not very good. So really, all of these steps don't actually make it secure on testnet because testnet itself isn't secure. So one thing that comes up here is, wait a minute, now I thought you said in the Sidechains white paper that Bitcoin's smart contracting system had to be improved and fixed before it could handle this two-way peg mechanism. And that's true. So in the Appendix A of the white paper, we describe this mechanism called a federated peg that is a sort of step-in alternative to the true two-way peg mechanism that works without any changes at all in the hosting network. So the way the federated peg works is that there is a federation, a group of these computers, we call them oracles in our parlance, that execute the same rules that we would like the testnet network to run, but which doesn't currently run because it doesn't have the support for it right now. So you can think of this like a centralized protocol adapter that allows the two things to talk absent native support. The federation uses a multi-signature, so it's an N of M threshold. And the participants in it have no discretion. Their rules are completely defined by the rules of the system. So the users of the sidechain can mechanically detect misbehavior. But if a super threshold set of the functionaries, or these parties with no discretion in the federation, are compromised, if they misbehave, then they can steal the coins that are currently in the sidechain network. So that's the limitation of this particular workaround. In the case of the Elements Alpha network, we're using a hybrid where the direction from the Elements network back to testnet uses the functionaries, but the direction from testnet into the Elements network is autonomously verified by the participants in the Elements network. So this work with the deterministic two-way peg and its implementation has been principally done by Matt Carlo, and it's described in more detail in the Sidechains white paper. So the next element I'd like to talk about is issued assets. So Bitcoin brought us this idea of smart contracts, these programmatic rules enforced trustlessly by the network. But ultimately, the Bitcoin network can only control the disposition of Bitcoins. It can't control the disposition of other assets. So you can imagine using smart contracts to build things like trustless exchanges for one asset to another. You could imagine using smart contracts to build derivatives, and many people have imagined these things. But since the Bitcoin network can only control things in it, it can't sort of reach out into the wider world and directly control things, thankfully. It means that in order for these smart contracts to be used, they have to be used with assets in the system. So if you'd like to build some kind of fancy synthetic asset with smart contracts, the network has to understand the component assets in some way. So an example of a synthetic asset would be something like I can create a token which could be redeemed for one car or some amount of Bitcoin which changes over time. No, wait, car? Right. So the way that you would make an asset in a cryptocurrency network like a car be an actual interesting thing is this idea called smart property. And the idea there is that you can build a car or a vending machine or some device which itself watches the Bitcoin network and uses information in the Bitcoin network to decide who its owner is, like which key will start the car. So there are other ways of doing issued assets in Bitcoin. There's a proposal called Colorcoin, which has been deployed for some number of years at various levels of use. But Colorcoins have a couple of problems. For one, they're incompatible with this communication-efficient payment verification mechanism, this SPV property in Bitcoin, which is pretty important when you want to do something like have a vending machine or a car decide whether or not its ownership has changed. You don't want the car to have to download the whole history of the Bitcoin network to trace ownership. Colored coins also result in the creation of many tiny amounts of Bitcoin in the network that are used for tracking value. Now, Bitcoin remains valuable so long as people want Bitcoin to be valuable, so long as the Bitcoin network exists, so long as people are using it. But a proxy asset for Bitcoin using color coins may lose its value. It may be that the car that it's representing in the system becomes destroyed. And with colored coins, there is no mechanism in Bitcoin to have a different retention policy for different assets. Fundamentally, colored coins are invisible to the colorblind network. So smart contracts in Bitcoin can't be made aware of the assets. You can't write a smart contract that says, I will trade 1 Bitcoin for 1 foo, because the network has no idea that a foo is involved in the transaction. Although color coins do have one advantage. If the color coin system was constructed correctly, it could have very strong censorship resistance. So since only the participants in a colored coin know which coins in the network represent which assets, other participants in the network couldn't block their transactions selectively if the systems were built that way. And existing colored coin systems aren't, unfortunately. So the idea behind the issued assets functionality in Elements is to explicitly tag all of the tokens in the network with an asset type. And this immediately lets you use the efficient payment verification mechanisms that Bitcoin has today. And then all of the accounting rules in Bitcoin just become grouped by asset type. So normally in Bitcoin, a transaction has to ensure that the sum of the coins that come in are equal to the sum of the coins that come out to prevent inflation. Well, with issued assets, that same grouping is applied per asset. So the sum of the cars that come in have to be equal to the sum of the cars that come out, or whatever the asset is. So to issue an asset on the network, you use a new special transaction type, an asset issuance transaction, and the transaction ID from that transaction becomes the tag that traces them around. So this is early work with just the basic infrastructure for it, but there's a lot of neat things that can be done on top of this. And this is mostly the work of Jorge Timon. So the next element I'm going to talk about is relative check lock time. So today in Bitcoin, transactions have a good after date, sort of time criteria after which the transaction is good, and before that the transaction can't be relayed or confirmed in the network. But many fancy contracts that people would like to create need a refund to avoid holdup. So if I want to place some coins into escrow that will be transferable out of the escrow under some conditions, I want to be able to ensure that if those conditions are never met, that the coin comes back to me after some amount of time. And so what a check lock time does is allows the contract rules in Bitcoin to specify a constraint on that good after date. So there's a current proposal, BIP65, to deploy an absolute check lock time in the Bitcoin network, and it may be available sometime this year, although we don't know when it will be deployed exactly because it has to wait for some other features to make it into the system. This absolute check lock time is immediately available in the Elements network, and so people can begin experimenting with it there immediately. Going beyond the absolute check lock time, it would be very useful to support relative times. So the idea behind for a relative time is that the clock starts ticking not at a fixed time, but when some other event has occurred in the network, particularly another contract or transaction. So in Bitcoin, each input coin into a transaction has a 32-bit sequence number. And the original idea was that you could increment this sequence number to update the transaction. Every time you issued a new version of the transaction, you'd update the sequence number, and then someone could take the final version to the network and get that one confirmed. But there was no enforcement of that monotone update rule in the Bitcoin system. And in fact, no obvious way that it could be enforced. And what this meant is that updating transactions this way was insecure. You could make an updated version of the transaction, but the person you were transacting with might have preferred an older version, and they could take that older version to the network and get the network to confirm that version instead, perhaps because it was more profitable for the network. And so you couldn't count on it to do anything useful. So what relative check lock time does is it redefines the operation of the sequence number field. So if the sequence number is at its maximum, you can spend the coin, you can spend the transaction at any point. If the sequence number is one less than the maximum, then the transaction has to be delayed at least one block from the block that created the coins that it's spending. If the sequence number is 2 less than the maximum, then it has to be 2 blocks later. 3 less than the maximum, it has to be 3 blocks later. The point is that as you increase your sequence number, you increase the earliest time at which the transaction can go into the network. And so this gives a real mechanism for enforcement that the latest version of the transaction is the one that the network takes. This is a technique used in the proposal called the Lightning Network to achieve very high scalability for transactions off the Bitcoin main network. So the next element that I'm going to talk about is called Segregated Witness. And this is somewhat of a technical name. So first I'll explain what we're trying to accomplish here. So in Bitcoin today, when you approve a transaction, what you're actually doing is providing a set of inputs that satisfy the rules, the contract, on the coins you're spending. You're saying, okay, these coins required a signature from me, and so here's my signature. Then the network checks the rules, and they validate that the inputs the transacting party provided match them. So this raises a question, well, what happens if you take a valid transaction in the network and you change those inputs? You reorder them, you modify them, you encode them differently in a way that they're still valid, but which changes the data in the transaction. So this can be done. And what happens is that it changes the ID number of the transaction. and nothing else. It doesn't change who the transaction pays. It doesn't change what the transaction does. It doesn't change its amount. It changes the ID number. And this sounds kind of benign. But in fact, changing the ID number breaks many applications of Bitcoin. It confuses accounting, and it also means that if you're making a multi-step sequence of dependent transactions, since each transaction refers to each other by its ID number, that chain of transactions is broken. And so it can be used by people to DOS attack the network. It can be used to make refunds ineffective. It's generally a real pain. And because of the way this flexible contract system works in Bitcoin, it's almost impossible to prevent malleability in it. And there's a proposal called BIP62, which tries to prevent malleability by defining exactly how the transaction needs to be encoded. And it's kind of complicated, and that's part of the reason that the proposal hasn't been deployed on the network yet. And we're not even sure that it actually catches all the potential sources of malleability. So a witness is a technical term from mathematical logic. And what a witness is it's a specific value that is concrete proof of an existential claim. Like if I say there exists an x such that f of x returns true, that value x is a witness. And you can think of the signature data, the inputs in a Bitcoin transaction, you can think of them as the witness for the validity of the transaction. And we use the word witness in part to distinguish this script sig data, this witness data from the transaction, from the basic digital signature system. So Bitcoin itself doesn't really care what the witness was that showed a transaction to be valid. It just cares that the transaction is valid. And so if you're not verifying the history of the Bitcoin network, you could potentially skip downloading all of these witnesses. You could potentially skip downloading this data. And it turns out that the witnesses are about 2/3 of the data in the Bitcoin blockchain today. But unfortunately, you can't actually skip downloading them right now because you need that data in order to compute and check the transaction IDs. So what Segregated Witness does is it changes the transaction ID formula in the system. And it separates the transaction into two parts: the witness, which is all of the script sig fields in the transaction, and the transaction itself, which is everything else. And it makes the transaction ID only cover the transaction itself and not this witness part of it. Now, the blocks in the Bitcoin network still commit to the witnesses that were used, and this is important for forensic reasons. If you want to check that a transaction was signed off by a particular set of its parties, like it was a 2 of 3 multisig, and you want to see which 2 approved the transaction, you need to go and look at the witness to check this. But the witness can be committed to in a block in a way that makes it easy to skip downloading it if you're not interested in it. So what this allows you to do is to synchronize the blockchain with the network when you're not checking the signatures without transferring that data, saving you 2/3 of the bandwidth. And it also completely eliminates unwanted third-party changes to the transaction IDs. So this has been mostly the work of Peter Willett. So the next element I'd like to talk about is script enhancements. I've talked a couple of times about this really awesome smart contracting capability in Bitcoin. It's achieved through this scripting language built into the system called Script. And Bitcoin Script was originally much more powerful, a bit too powerful, in fact. It allowed people to crash nodes and to steal coins, which most people regarded as undesirable. So what happened was that these bits of excessive power were removed with some emergency repairs to the system, where many operations in Script were disabled. And disabled is basically a euphemism. They were removed completely. Now, these operations weren't technically hard to fix. They could have just been fixed instead, but it was kind of an emergency, so they were removed. And they could be restored to the system without much effort, especially if you didn't care about compatibility with the existing network. But there's something of a catch-22 here. No one's using functionality that isn't there, and it's hard to justify the cost and effort and risk for putting in functionality that people aren't using, and then we're not completely clear which of the functionality they will use. People have also talked about a replacement, much more powerful smart contracting system for Bitcoin that has a bunch of interesting properties for some time, but that's a longer-term effort, and it's not clear when that'll be finished. So when we look at the element system, well, the whole idea is that experimentation is cheap. So why not experiment with turning back on the script operations there? So that's precisely what we've done. In Elements, there's a set of script enhancements that, for one, re-enable all of the disabled opcodes in Bitcoin script, which is things like concatenation, substring, and bitwise operators like AND/OR, XOR. And there's a tremendous number of things you can do with this. For example, you can make an efficient, like 100-byte signature, 1 of 1,000 multisig using this mechanism. You can also do things like build trustless lotteries, and, well, I'm not sure. It'll be interesting to see what people do with it. While doing these enhancements, we also replaced the base signature system in Bitcoin, which is ECDSA, with Schnorr. Now, Schnorr signatures are a different approach. We're using the same cryptographic curve, but Schnorr has a number of advantages. For one, the security proofs for it are much stronger and more convincing. Schnorr also supports an efficient multisig, where you can do a 20 of 20 signature with the same amount of data as a 1 of 1. Schnorr also supports efficient batch verification, so the network can verify many transactions at once, much faster than it can verify them one at a time. And this is roughly a 2x speedup. We also added the capability to check signatures on data coming in on the stack, other than the transaction data itself. And what this allows you to do is to build bonds on good behavior. So you can say that here's some Bitcoin in the network, and it can be paid out to someone if they can prove that a third party signed the same contract twice when they were only supposed to sign it once. So this has been primarily the work of Patrick Straitman. Speaking of signatures, in Bitcoin, the signatures and transactions only directly cover the amount that the transaction is moving indirectly by signing the transaction ID of the originating coin. Now, this has the effect that if you have some hardware wallet device that has rules or conditions on the amount of coins that it's allowed to move or the fees that it can pay, the only way it can enforce those rules is by having you prove to it what the value of the transaction is by streaming in all of the input transactions into the device. And you can contrive cases where the amount of data that you'd have to stream in to prove the values to a hardware wallet could be as much as a gigabyte of data, which is a little bit ridiculous. So if you're not worried about compatibility, there's a simple, straightforward fix to this. You change the signing algorithm in Bitcoin so that the signature directly also covers the amount of the coin that it's spending. And then if you lie to the device and tell it that it's spending a different amount than it is, the signatures it produces won't matter, or they won't be valid, and so it doesn't matter, and the transaction can't go through. And so the rules can be enforced then. So this has mostly been the work of Glenn Willen. So the next element I'd like to talk about is federated consensus. Now, Bitcoin, as I mentioned, uses this decentralized consensus, which is absolutely essential for upholding Bitcoin's value and ethos in the wider world. It's what makes the system resistant to outside influence and to political meddling, and what makes it trustworthy. But this decentralized system, well, it's hard to say that it even works for sure in Bitcoin. And so it's much harder to apply it to other kinds of systems. So if you wanted to make a parallel Bitcoin network with different properties or different users, maybe the Bitcoin decentralized consensus system doesn't work. Or really, if you're talking about a private system, what does decentralized consensus even mean? So it's not clear that it's possible to use decentralized consensus in an experimental, low-value, or small system. And even if you were trying to use decentralized consensus in a new system, how do you bootstrap it? Because the decentralized consensus is only secure with certain economic incentives in place. So there are many other mechanisms for consensus that people have proposed in the wider world. In the Sidechains white paper, we sort of formalized Bitcoin's consensus by calling it a dynamic membership multi-party signature. And the idea there is to say that the blocks in the Bitcoin network are valid if more than a threshold of parties have signed them. Which party? Well, the which is dynamic in the Bitcoin system. So what happens if you take that idea of a dynamic multi-party signature and replace it with a static, ordinary, plain multi-party signature? The result is a centralized security model, but one which is better arbitrarily than just trusting a single server. It's a system where you can have real-time auditing by all participants, and where most potential dishonesty is machine detectable. The counterpoint, though, being that censorship is not machine detectable in that model. You can build this with an arbitrary multi-sig policy, so you can decide what your security and risks are in it. So you can have a rule that says that the blocks are valid if an auditor and 5 of 8 sign off on them, or if 8 of 8, where these of 8 are some set of parties that you trust. So this approach doesn't require any human discretion, and you could potentially implement it on tamper-resistant, tamper-detecting hardware to make it more secure. And some applications need trust, and trust is inherently a bit of centralization. But if your application, say you're trading around a digital proxy for gold, requires someone to eventually redeem those digital tokens for gold, well, you have to trust that party. And so if you have trust, why not make use of it? So this has been mostly the work of Jorge Tamán. The next and probably most complex part of the features that we've put into Elements is this functionality called confidential transactions. So traditional transaction systems for money provide, among many other characteristics, privacy. So when you transact with money in the bank, the only parties that normally learn about your transaction are you, the bank, and the party you're transacting with, and maybe whoever the bank decides to tell. But the rest of the world doesn't learn about your transactions. And they don't learn about your bank balance. They don't learn about who you're trading with. And this is actually essential for both commercial and personal use. Without a basic level of privacy, thieves can target parties that have lots of money. Fraudsters can see the flows of transactions and use that information to con people. The negotiating positions in commercial deals can be undermined. If your competitor knows what your margins are, or your counterparty knows how much you can spend, right? If your landlord knows that you just got it raised, well, they can try to hit you up for a bigger bit, and they can tell you, well, I know you're good for it. The loss of privacy also breaks fungibility, which is an inherent characteristic of any money-like good, that one Bitcoin is just as good as any other Bitcoin. But if each Bitcoin has a history where people know how it was used, maybe some people won't want some Bitcoins. So it's often presented as though there's a conflict here. Bitcoin has this decentralized system where the network acts as the bank approving transactions. And the bank normally can see all of your transactions to know that they're valid. So people say, isn't it the case that the Bitcoin network has to also see the transactions, and by extension, the entire world has to see the transactions? But surprisingly, this isn't the case, and that privacy is actually completely compatible with public verification. An easy example of this is digital signatures. And what a digital signature does is it allows you to sign a document using a secret key known only to you, and your signature proves that you know the secret key and that you approve the document, but it doesn't disclose anything about the secret key to the rest of the world. And so verification doesn't have to be in conflict with privacy. We just need the right technology. So Bitcoin, from the very start, uses pseudonymity to handle the issue of privacy. And the idea is that Bitcoin users, rather than having persistent identities, would use single-use addresses, and they'd throw them away after use, and then you wouldn't know which address belonged to which user, and you'd have some level of privacy. But it's turned out in practice that this approach is very fragile. And particularly when you pay someone, well, they know who you are by virtue of transacting with you, and then they can look at your transaction history and the addresses you've used to make a good guess at what your finances are. And if you reuse your address for convenience reasons, then it ends up leaking this information to everyone. And all they have to do is attach your name to one address, and then they get most of the information. And this lack of privacy is often cited as a concern by many parties. So when we ask other institutions about using Bitcoin, it's often frequently cited. And I'm not kidding here. Even the most boring traditional institutions look at this and say, I don't want to be transacting in a way where all of my moves are telegraphed by my transactions. Often in Bitcoin, we like to talk about the advantages of transparency, because one thing you get out of a highly public ledger is the potential for lots of transparency. But transparency is a tool that cuts both ways if it's not under the control of its users. Transparency, not controlled, can exacerbate power imbalances. Like, a government can maybe afford to go micromanage and check all of your spending, but you can't spend the time to go and check its spending. And so transparency isn't always useful. Also, data is not wisdom. And so when you receive this deluge of raw information from the network, this transaction, that transaction, it doesn't necessarily meaningfully tell you anything. Real transparency requires a conscious effort. And finally, some people worry about harmful uses if there's too much privacy, but harmful uses exist today. And the people performing harmful things, stealing people's money or other activities like that, can have privacy. They can already buy their way into ways of transacting that are sufficiently private for them. More than anything else, though, when I think about this, I look to the example we've seen at the internet in large. When I work in the IETF with other people who've been longtime developers of the protocols on the internet, there's now an almost ubiquitous regret that we made a mistake in building an internet where encryption wasn't the default and always on. And there was always a reason for this, that we didn't make encryption the default on the internet, right? It's complex, encryption is slow, it's incompatible with the things that are deployed now, and these are all completely true. But when we look at this history with the benefit of hindsight, we see those reasons were insignificant. And if we've taken the cost 10 years ago to make encryption the default on the internet, it would be no big deal today. And as time goes on, it becomes harder and harder to deploy pervasive encryption in the internet. And this is universally regarded as a regretful, bad scenario by all the people who work to build the protocols. So I don't want to make the same mistake with money. So I think to myself, if Bitcoin were to displace other systems of money, would I want to live in that world? And without improvements on privacy, the answer is no. So there have been many proposals to improve privacy in Bitcoin. It's not only me that thinks this is an issue. I classify them into two groups, the compatible group and the cryptographic group. A compatible group I describe as features that work without change in the existing Bitcoin network. And there are proposals like CoinJoin and CoinSwap, which are both proposals of mine. People using centralized privacy-generating servers. Then there are these cryptographic solutions, zero coin, one-way aggregate signatures, the traceable ring signatures of Bitcoin and Monero, zero cash. The compatible solutions usually suffer from very weak privacy, and their privacy is fragile. And usually the problem is that the amounts transferred in the transactions sort of unmask or break the privacy that they provide. The cryptographic solutions, on the other hand, generally have this problem where they break this functionality in the Bitcoin system called pruning. What pruning is a Bitcoin's node's ability to forget the past, so that it can validate a new group of transactions without remembering all of the transactions that came before it. And so pruning is essential to Bitcoin scalability. You need to be able to have nodes forget about things that are already done and over with. But cryptographic systems which hide which coins have actually been spent break pruning. They often need strong new cryptographic assumptions, which may turn out to be broken, and they often have poor performance and/or just aren't implemented. So most of the prior work on cryptographic privacy in Bitcoin has focused on protecting the transaction graph, the flow of coins from one party to another. You can liken this to metadata for phone records or for internet traffic. And so it's a little funny because for cryptographic privacy on the internet, we often don't do anything about metadata. Now, metadata is important to make private, but it's usually almost impossible to make private. So what if in Bitcoin, instead of protecting the metadata, we protected the content? What's the content? A transaction's content is its destination and its amounts, how much is being transferred. Now, if you use the pseudonymous addresses and don't reuse them, your destinations are already private, but the amounts are not private. Well, it actually turns out, if you think about it, in most scenarios, it's the amounts that are more important to make private. I mean, when you transact with someone, they know who you are, but they don't know what your finances are. They don't know your balance, and that's what you'd like to keep private. So it's possible to do this. And what we do is we replace the amounts in Bitcoin transactions with these 33-byte commitments. And a commitment is like a cryptographic hash. And they're blinded, which means that they're obscured or scrambled by a blinding key. And the commitment scheme we use is one that preserves addition. And that means that it preserves the property that a committed value plus another committed value is equal to the commitment of the two values. The network can verify that the amounts add up. So this approach was originally proposed by my co-founder Adam Back in 2013 in a Bitcoin talk thread called Bitcoins with Homomorphic Value. But there are some challenges in making this actually work. In order to make this system work, you have to deal with the case that an output of the transaction could potentially be negative. So remember, we're trying to verify the invariant that the sum of the inputs equals the sum of the outputs. So you can think of a transaction spending a 1 Bitcoin input and a 2 Bitcoin input and creating, as its outputs, a negative 10 Bitcoin output and a 13 Bitcoin output. So both sides of this equation, 1 plus 1 is 3, and negative 10 plus 13 is 3, and so they add up. And what that did was it created a whole bunch of Bitcoins out of thin air. To prevent someone from creating negative value blinded outputs, we need something called a zero-knowledge range proof. And that's something that allows you to prove to someone that a blinded value is within some range, but without actually specifying what the value is. Now, there are many techniques in the literature for range proofs, but they have challenges in efficiency. So I invented a generalization of cryptographic ring signatures and a number of other optimizations in order to make range proofs which are more efficient. And I built a system where you can decide how private you want your outputs to be by choosing how large the range proof is, and where the range proofs also have an exponent, so you can pick what precision the range proof is specifying the value in. And so you can build a 32-bit range proof, which is large enough for a 42 Bitcoin or 429 Bitcoin or 4,249 Bitcoin amount, depending on what you've chosen for your precision. And you can build one of that size in 2.5 kilobytes, which is small enough that we can realistically use it in the public network. I then came up with a scheme that lets you take that same 2.5 kilobytes and sort of double use it to deploy it again for another application. And what you can do is use that 2.5 kilobytes to communicate a private message to the payee of the transaction. So the sender can create a message that's private and only the payee will receive it, and they can sort of slip it into that 2.5 kilobytes without adding any additional size. And this is about 80% efficient, so most of the size can be used for this. And people often want the ability to add small messages to Bitcoin transactions, and it's been a little hard to stomach that in the public network where it's adding cost to all the participants in the system. But if they can get it as a side effect of their range proofs, great. So this approach is compatible with watching wallets, which is the ability for you to share a key with a third party so they can audit your transactions and see the payments coming into you, but without the ability to spend your coins. And it's also compatible with transparency because you can share blinded values with whomever you want to prove that a payment was a particular value. And so you can be as transparent as you want to be and be as private as you want to be. So this has been primarily my work. So where do we go from here? I'm personally planning on continuing to refine and improve these elements and to create many more of them. And I'm looking forward to see what happens in the test network. It is a test, and so I expect that it will blow up in interesting and new ways. I'm quite sure it will. I'm very curious if other people will see and appreciate this potential to introduce new technology to the Bitcoin ecosystem without seeking permission or rebooting our network effect, without restarting our adoption. And if this potential will bring more development to the space. Well, I don't know if it will, but I look forward to finding out. Thanks.